It's a real pleasure for me to introduce to you my friend and colleague, Gary Gladding, who is Professor of Physics here at the University of Illinois and also our Department Associate Head for Undergraduate Education, a critical and pivotal role position in the department. Today, Gary has kindly agreed to explain to us why our time is not his time. Please join me in giving him a very warm welcome.
Thanks, Paul. I realize I probably prepared too much stuff here, so I think I'm just going to jump right in, see where we go. So the title is My Time Is Not Your Time. Refers to a song that you young people would never have heard, but that's all right. Okay. What I want to do today, yeah. A little bright. They say no. They say no, so we better do it, okay? So we'll see. Hopefully this is going to work. Okay, so the talk says Einstein's relativity in theory and practice. The theory part turns out to be most of the talk. And what's the goal of this thing? Well, what I want to do in this talk is not to present you bunches of facts you can take away and impress all your friends, okay? That's not my goal. My goal, in fact, is to try to teach a little bit, okay? My goal is to try to present the physical arguments that, as I say here, illustrate and motivate the theory of relativity. It is true that maybe you've heard that one person understands the theory of relativity. Well, that was probably true at one point, okay? But after 1905, a lot of people can understand the theory of relativity, and I claim that important pieces of it can be understood at a very, very rudimentary level. So now there are certain, I was told to give you some references. So first there's a book. Where's the book? Here's a book. Einstein himself wrote a popular book here. It's called Relativity, a clear explanation that anyone can understand. So there, you see, anyone can understand it. It's interesting, actually, it was written 19, whenever it was, 15, 19, something like that. And popular science sounds a lot different than then, but it's a good book. The other thing you can do, I'll plug, as long as we're plugging websites here, I've taught a course here for non-scientists, which is colloquially known as Physics for Poets, and the whole course is on the web, and a lot of the things that you're seeing today I stole from my own course that's on the web. So not only are there lectures, there are homeworks, there are exams, there are anything, more things than you would like to know. So this particular talk, a lot of it you can find at that website. And finally, when I get to the end, I should talk a little bit about Einstein's theory in practice. In other words, after convincing you it's a good idea maybe, but kind of crazy, and therefore is it really happening in our world, I'll give you some examples. Relativity in daily use, right? That's because it is. And I thought of a couple of examples. One, which is sort of becoming now standard technology, the global positioning system. And you know, it's kind of amazing, actually, that for that thing to work, you actually have to need relativity. And then finally, in the stuff that I do for my research in particle physics, this is like daily stuff. This is like plumbing. This is not esoteric. This is what you got to do. If you don't do this, it doesn't work. So I've listed here sort of three general websites. One from Berkeley, and sort of called the Particle Adventure, and it's very nice and got a lot of good graphics. The experiment I'm currently working on, we have a website here to take a sort of a virtual tour of the lab. It has videos in it as well. And finally, there's an experiment done by some of my colleagues here at the University of Illinois, which I think is particularly relevant to what we're talking about. So I'll end with that one. So there's the man, okay? So you've probably heard of him, okay? His brief history, he was born German and went to university in Switzerland and became a citizen. Then, as you probably also have heard, he started out in the patent office and did physics on the side. We don't do that anymore. And then there was this famous year, 1905, in which he published 5 incredible articles, okay? Almost any one of them could have gotten him the Nobel Prize. In fact, the Nobel Prize was not won for relativity, okay? It was won for the photoelectric effect, which was an important part to the beginning of quantum mechanics. But at any rate, there are 5 incredible articles in 1905. So after that, it ceased to become a part-time job. He became a professor, but it wasn't immediate, by the way. And then finally, in 1916, he wrote General Relativity. What I'm going to be talking about here almost exclusively today is what we call special relativity, and that he is basically covered in these two articles in 1905. Okay, so I want to start out with the way he starts out, actually, thinking about something called simultaneity, things happening at the same time. It would seem that two things either happen at the same time or they don't, right? I mean, there are only two possibilities. We have a small, it's tough to find demonstrations in relativity, let me tell you. It's really tough. So, so what we decided to do, something like this. Let's see if this works. Okay, so we have two light sources. Now, if I say that this is, we'll call event 1 and this event 2, and I want to ask the question, do they happen at the same time? And so if I say, do they happen at the same time? You say, no, no way, all right? Then I go, those happen at the same time? How about that? Pretty good, right? Okay, well, it's tough to tell, right? There's some flashes of light. You can imagine I should bring out some more fancy equipment to try to determine whether or not those things happen at the same time, okay? But Einstein says, well, wait a minute now. Until we define what we mean by things happening at the same time, especially if they're not at the same place in space, I don't know what it means. You do, but he doesn't, right? And what he wants to distinguish between is the simultaneity of local events. Now, local events would be, for example, let's define these things. All right. When I push the buttons, these two things, my pushing, those events, I consider those to be local events, all right? And determining whether these happen at the same time or not, I consider to be a sort of primitive judgment that I can make. If these things happen at the same point in space, simultaneity is what we mean. It's just a primitive concept. I can't talk about it anymore, okay? However, when I talk about the flashes of these strobes that are separated from me in space, and I try to make them happen at the same time, now what Einstein says is I have to define what I mean by the simultaneity of spatially separated events, okay? So that was our local events. And here, we need what is called an operational definition. In other words, what we need to do is to tell you a set of operations such that I can determine whether those two things happened at the same time or not. Once I do that, then I know what it means, it's defined, and then I just have to go out and try to do it. So here's what Einstein does, and it's a very reasonable thing. Basically, he says, okay, if I have two events, and the events are going to be strobes flashing, right? So, boom, boom. Now, what I'm saying is if I position myself halfway between these two events, and then I don't know how I'm supposed to watch these things, okay. Excuse me, okay. And then if I judge whether light from those two events reaches me at the same time, I've reduced the statement about what's happening at spatially separated points to a statement about what's happening here, where I am. Okay? So I've reduced the spatially separated concept of simultaneity to the local determination of simultaneity. Okay? And so it sounds right. And if I'm going to do that, I should be halfway between it. I mean, if I were over here, and I said, okay, I'm much closer to this source, I'd think the light should get to me quicker than the light from over there. That would be a bad definition, right? So, I mean, it sounds reasonable that what you want to do is be halfway in between, okay? So that's what he does. So I've made this little graphic here of Mr. O. In physics, there's always a Mr. O, right? So there's Mr. O, the observer. And, but Einstein says, now, that's fine, but now let's think a little bit, okay? If that's our definition, what if we had another observer, we'll call him O prime, and suppose O prime is moving with respect to O at some velocity v. What Einstein wants to ask is, if both O and O prime apply the same definition, they play by the same rules, what are they going to get? What's their answer going to be? Okay? Well, let's just suppose that when I flick these things, I get the light at the same time. Therefore, I'm going to say those two light things happen at the same time. Let's just assume that's happened. So, but if that's true, the question is, what will O prime say? Now, I mean, O prime is now, okay, all right, sports fans, let's see if we can do this. All right, without tripping over all these things. See, now I'm now O prime, and as I as I come by, Mr. O is still there. You can't see him, but he's still there. Believe me, okay? And now if I'm O prime, as I come by, when we happen, okay. Well, that wasn't very good, was it? Let me try it again. Now, as I go by, okay, I'm moving. I'm moving. Now, if the speed of light isn't infinite, right, when the light flashes, it takes some finite time to get to me. Now, if I'm moving relative to this guy, then if they arrive at the same time to this guy, they can't possibly arrive at the same time for me, right? Isn't that right? So here's a little picture, try to convince you of that. Namely, in the time it takes light to approach Mr. O here, Mr. O prime, who in fact is moving toward event B and away from event A, will intercept the light flashes from A or from B before A. And therefore, O prime would say, okay, I got the light from B before A, therefore B happened before A. And O will say B and A happen at the same time. You see that? It's clear, right? So who's right? Right? So you got to go to Judge Wapner or somebody. You say, hey, who is right? Well, let's see. O says that A and B happen at the same time because he applied Einstein's definition of simultaneity of spatially separated events, and the light signals from A and B arrived at his person at the same time, therefore they happen at the same time. O prime says, no, he received the light from B before A, and therefore B happened before A. Okay? Now, how do we resolve this? Well, O says, well, I know, hold on, I know what's going on. You know, O prime has all sorts of good intentions, but he was just confused, right? Because after all, O prime was moving. Now, if O prime had just stood still, it would have turned out that he would have known that A and B happen at the same time. But because O prime is moving, he gets the wrong information. Okay? So I understand, I mean, O prime is not lying to me. O prime thinks B happened before A, but in fact, they really happened at the same time. It's just that he was moving, and that kind of screwed him up a little bit. Okay? So the question is, how does O prime respond to this argument? All right? How does O prime respond to this argument? Well, O prime says, you know, I wasn't moving. You know, I never move. Right? I always am where I am. I can't leave myself. Right? So therefore, it's that other guy. O was moving. Right? Because O prime can simply say, I was sitting here, and O, and the rest of you people, were moving past me at velocity v. Okay? And that, because Mr. O was moving, he got the wrong answer. Okay? In other words, since Mr. O was moving, he was fooled into thinking that those two things happened at the same time. I mean, I was just sitting here, those two events happened, I got the light from B before the light from A, and therefore I know B happened before A. But, you know, that O guy, O was moving, I know it's unusual, but O was moving toward A and away from, that's the later event, away from the earlier event at just the right speed so that he got the light at the same time. And therefore, he mistakenly thinks that A and B happen at the same time. Okay? So you're the judge. You're the judge, and we've got O's case, and you got O prime's case. Who are you going to believe? There's the picture of it, what I was trying to say. Who are you trying to believe? What do you think? Who do you think? I mean, what are the options here? Okay? Who is right? Let's take a quick vote. So you're the judge. You've heard these two arguments. O says A and B are simultaneous. O prime says B happened before A. So just to see where we are. How many people think that O is right? The two events are simultaneous. Thanks a lot. Okay. How many people think, yeah, OJ did? No, O is right? Got that from the audience. Okay. How about O prime? How about, I have no idea. There we go, okay, right. Because actually, both of those arguments sounded pretty good, didn't they? Pretty good. I mean, I hope I tried to make them sound good anyway. So if you look at who is right, we got three possibilities. We got O is right, O prime is right, or both are right. Can both of those people be right? Good question, right? Why would we have a hard time saying that both of those guys are right? It's because we think we know what time is, right? We live in time, right? We experience time, and we have, I think, a very good common sense notion of time as being a river, something that's absolute, something that's out there, something that we march through, right? There's the past, the present, the future, and we just move right through that time. Time is out there, kind of independent of us, right? Just sitting there. It's a stage in which we do our thing. And therefore, it would seem, I would think, that what we want to say is that either A is right or B is right. I mean, you know, either these things happen at the same time or they don't. And it might be difficult to determine, but hey, you know, in the bottom line, either they happen at the same time or they don't. Now, if that's true, if we have to choose between these two arguments, we have to single one of these people out. We have to say O or O prime is special in some way. We're going to give them preferential treatment, right? They are not equivalent. One of these guys is right. I mean, basically, the idea is that O says he's right because O prime is moving, but O prime's argument is that O prime is right because O is moving. So for me to choose between the two, I have to say one of them is really moving and the other one isn't. Okay? Or something like that. I've got to do something to distinguish the two observers. Now, the problem is that, try as we may, we have had no experimental evidence which supports the idea that we can distinguish O from O prime in this way. There are many ways of talking about it. The usual experiment that's cited at this time is the Michelson-Morley experiment, Big Science of 1887, in which was looking for how fast the Earth is moving with respect to the absolute frame containing the ether at rest. Okay? And that was an experiment which failed. It failed. It means it could not determine how fast the Earth was moving with respect to the ether. And in any other thing we've ever been able to do, there's nothing that allows us to pick out such a preferential reference frame, if you like. But if we accept that, then we're forced, I think, to C. And C says both are right. And if that's true, okay, then that makes us happy. We're making lots of people right. That usually makes people happy. That's what I'm learning as associate head, Paul, by the way. Okay, anyway, you can make lots of people happy. But what happened is that if we do that, we have to give up something. There's a price, okay? And the price we have to pay is we have to abandon our notion of time as a river. Okay? Time no longer can be an absolute quantity. You have a time and I have a time. If we're moving with respect to each other, those times are not the same. Now, so what does Einstein say? Well, Einstein solves all these issues in actually only making two assumptions. He called the two postulates in the 1905 paper, and that's all we need to know. First is something called the principle of relativity. And the principle of relativity, in his words, is what? The phenomena of electrodynamics as well as mechanics possess no properties corresponding to the idea of absolute rest. They suggest, rather, that the same laws of electrodynamics and optics will be valid for all frames of reference for which the equations of mechanics hold good. Kind of long-winded, but the big idea is that the results of experiments are independent of the translational motion of the frame of reference in which they are performed. Okay? In other words, for example, I mean, if you're in an airplane and you're moving and, 400 miles an hour or something like that, suppose you want to pour a cup of coffee. If you don't think, you pour a cup of coffee. If you think and you say, I'm moving at 400 miles an hour, by the time I actually pour it, I'm going to be over there. So let me try to get it up there and I'll catch it, okay? I mean, that isn't what you do, right? Well, because what your body knows, okay, that you don't have to do that. And what that means is there's really no way of knowing whether you are really moving or not. Your reference frame is just as good as any other reference frame. You don't have to have a special physics book for your reference frame. There's only, I guess that hurts the publishers, doesn't it? You only need one physics book for all reference frames. You can take that same physics book on the airplane with you and use it to do experiments, and you'll get the same results as you would on Earth. assuming that you don't run into turbulence, right? Okay. So that's the first one. That's called the principle of relativity, which basically says O and O prime are equivalent observers. There's no way we can distinguish between them. And finally, there's this thing about the speed of light. Light is always propagated in empty space with a definite velocity we usually call c, which is independent of the state of motion of the emitting body. That is to say, the speed of light is equal to c, a number, with respect to everybody. That's a little funny. It's something you're not quite used to, right? I mean, usually we say if I'm on that airplane, okay, and I poured a coffee, you say the speed of the coffee is kind of slow. But someone on Earth would say the speed of that coffee is pretty fast, right? So you'd think that, you know, the speed should depend on your own reference frame. Light appears to be something a little different. The speed of light is always the same in any reference frame. And the interesting thing is, that's all we need. If we assume these two things are right, then we can effectively do all of special relativity. Okay? Now here's a way to try to calculate quantitatively why my time is not your time. So here's something we call the light clock. Suppose you have a light pulse that's emitted here at this source. It moves up to a mirror, bounces off the mirror, and comes back down. Pretty exciting, huh? Pretty exciting. And so what we want to do is we want to time that thing. And we want to compare two cases. What happens, how long does it take if we observe this when we're not moving with respect to this light clock, and we observe it when we are moving with respect to this light clock? Okay, I said that a little differently. Another way of saying it is two different cases, one in which the light clock is moving, one in which the light clock is fixed. Okay, but really, the light clock's the light clock. The light clock never moves, right? It's what we say. Are we at rest with respect to the light clock, or are we moving with respect to the light clock? So let's see, here's some cheap and dirty animation here, okay? Here's what happens. Cool, huh? So what have I done? That's what happens, right? That light clock moved with a certain velocity in one case. It was stationary with respect to the other case. And what happens is, not surprising, it left behind a little magenta track, right? So that was the trace of the light. That's what we see. Now, I think at this point you can see we have our problem, or we have the ability to calculate the difference in time, depending on your point of view. Because in this reference frame, the light covered this distance, up and back, 2w. In this reference frame, the light clearly covered a longer distance. Okay? Ordinarily, that's not a problem because we say, but it was going faster because it was moving with respect to us. But now, if we say light travels at the same speed, here we have a longer distance. How is that? If it travels at the same speed, it's got to take a longer time. So if we had a clock over here that's going to register the return of that light pulse, the clock here and the clock here cannot read the same. In other words, the clock that I read when I'm moving with it and the clock that is fixed with the ground while the light clocks move by it cannot read the same thing, right? It's real easy to see because those distances are different and the speeds are the same. Therefore, the time's got to be different. Now, that's really all there is to it, and you can actually use, I'll leave it as an exercise for the student. Okay, you can go home and try to sketch out the geometry that's involved here, and you ought to be able to derive this most important equation. And that most important equation is that moving clocks run slow. The time it takes the light to go up and back in the light clock frame is equal to the time it takes in the lab frame divided by something called gamma. And of course, I forgot to tell you what gamma is. I just realized this, okay? Is that right? Yeah, so I'm sure you can derive this equation. Since I didn't tell you what gamma is, you can derive any equation you like as long as you don't tell them what the things mean. Gamma is, oh, wake up. Gamma is 1 divided by the square root. Now this will test my true ability here. Okay. Oh, wait a minute. This is why at this point, do I have it? Yes. This is why at this point what we really want is John Madden. Okay? Gamma is equal to 1 divided by, hey, that's pretty good, square root 1 minus, beta squared. And all I got to do is tell you what beta is. And beta is equal to V divided by c. So v is the velocity that the light clock is moving with respect to you, and c is the speed of light. So ordinarily, beta is a very, very small number, right? You don't move at speeds close to the speed of light. And then if you square it, you get even a really small number. And then you take 1 minus that really small number, take a square root. Gamma is pretty much 1 for ordinary things. So beta is close to 0 for ordinary velocities we're concerned, and gamma is close to 1. Okay, but I claim that this formula comes directly out of this just by saying distance equals rate times time. Okay, you can do that in the quiet of whatever. Okay, so now there's a possible problem here, though. And the problem is, have we just violated the principle of relativity? In other words, I just told you that the time on the moving clock was different from the stationary clock. But after all, the whole purpose was, you know, what do you mean moving? Right? I mean, if I just switch reference frame, the other clock is moving. So it sounds like, well, we just did a nice little derivation, but it's got to be totally wrong because it's got to violate the principle of relativity. So is that true? Well, it's not true. And to try to prove that to you, I use what is called the double light clock. Whereas we have 2 light clocks now. We have the orange one move at velocity v with respect to the blue one. We have light pulses emitted by these 2 clocks, A2 and B2, at the moment that B2 passes A2. We call that event 1. Then event 2 happens when the light returns to the blue clock, all right? And event 3 happens when the light returns to the orange clock. So this exciting thing is broken down into 3 events. Both light pulses leave, light pulse returns to blue clock, light pulse returns to orange clock. And I've taken these pictures all in the reference frame of the blue clocks, right? I've called them the stationary ones. But if you do this experiment, you can do this calculation yourself, and what you'll find is that, after all, it's just what we just did. The light clock just turned upside down, that what we have are 2 events between the time between events 1 and 2. It's the blue time that is the smallest. In the interval between 1 and 3, it's the orange time that is smallest. Gamma is always greater than 1. So what's important here is not time, but time intervals between 2 events, okay? And what distinguishes the orange frame from the blue frame, it's okay to distinguish that for particular sets of events. I say here for events 1 to 2, the blue frame clock, that was A2, ran slow. And for events 1 to 3, the orange clock ran slow. And the difference is that the smallest time interval for a given 2 events is always measured in the frame in which only 1 clock is needed to make the measurement. Okay? In other words, if I define 2 events, there is a reference frame there's usually a reference frame in which those events happen at the same place. Okay, now, those 2 events you say didn't happen in the same place. One happened here, one happened here. Right. But, let's see if, okay, let's see. Oh, here we, I guess we do it. But this event and this event, they happen here and here, right? But to me, they both happen right here. Okay? So my reference frame would be the proper frame for those 2 events. Because I was present at both 2 events, I only needed 1 clock to measure that time interval. I measure what is called the proper time. Anybody else, like you guys, are going to measure the improper time. Not that it's wrong, it's just different. And it will be bigger by this factor of gamma. And that's really all there is to it. So once we have the concept of proper time, in other words, for a given pair of events, there's at most 1 reference frame in which those 2 events happen at the same point in space. And then that reference frame is, in fact, special. It's special for those 2 events only. And for those 2 events, it measures the proper time and measures the smallest time. All other reference frames measure a larger time and measure it larger by this factor of gamma. At ordinary speeds, this gamma is so close to 1 that you can't tell the difference. And that's why we think time is a river. Okay? But it doesn't have to be. Now, let's see. What about lengths? We're changing time. What happens to space? Well, we need an operational definition of length too, and you can get an idea that it's probably going to change, because if time is relative And the speed of light is absolute. And speed is distance divided by time. Sounds like space has got to be a little bit relative also. And in fact, it does. And let's leave just another exercise for the student and to try to derive that by thinking up an obvious definition of, operational definition of measuring the length. And we get the following thing. These are the final consequences of Einstein's two postulates. Namely, that for any two events, there's at most one frame of reference in which those two events happen at the same point. That's called the proper frame for those two events. It measures the smallest time. All other frames measure a larger time by a factor of gamma. Right? If I take something like this pointer and it moves by me, the length I measure of it as it moves will be smaller than the length I would measure if it were at rest with respect to me. It's by this absolute same factor of gamma. If something is moving in this direction, this distance, which is perpendicular to the motion, remains the same. All of those things are simple consequences of Einstein's two postulates. Now, what that means is the world is a little weird, and we usually illustrate this weirdness with some so-called paradoxes. One of the first ones is the famous garage paradox. Because after all, just think about it. If things really shrink as they move, then maybe you can make big cars fit in small garages if they go fast enough. Right? Why not? So this is the question. If a long car goes fast enough, will it fit into a short garage? Well, let's just put in some numbers. If you assume that the car is 15 feet when I measure it when I'm at rest with respect to it, and the garage of interest here is only 10 feet, no way, right? But if it goes really fast, suppose this car went 4/5 the speed of light. That's moving, okay? Then that's beta is 0.8, and gamma is 1 over the square root of 1 minus 0.8 squared. That turns out to be 5/3, okay? And so here we go. Let's see what happens. The answer from the garage attendant says, you know it. It'll certainly fit, because the length that I'll see this car is just going to be 15 feet divided by gamma. 15 divided by 5/3 is 9 feet. No problem. That's shorter than 10 feet. It'll fit. Okay? The car driver says, no way, no way, no way. Because, after all, the car driver says, that teeny garage is moving toward me. So it's even teenier, right? So it's 10 feet divided by gamma, which is only 6 feet. So how can my 15-foot car fit in a 6-foot garage? You don't know. How's it going to work? Who is right? How can you decide? Well, what do you do? Well, you have to analyze it. Now, you know, right now it sounds a little weird, right? Because it almost sounds like this simultaneity thing in which both of them could be right. But how can both of them be right? Somehow that just doesn't sound right. Either the car fits in the garage or it doesn't, right? Well, let's see. What we want to do is analyze this in terms of events. Don't think about time. Think about events. So event 1 is this. The front of the car passes the front of the garage. Event 2 is what? That's... Okay. Hokey, but it works. The front of the car reaches the back of the garage. All right? And now we can calculate. These are two events. Event 1, event 2, what's the time interval between these two events? And so what the garage attendant says is a point, the front of the car, traveling at 4/5 the speed of light, traveled a definite distance, 10 feet. That's the length of my garage. And the time it took was, well, just the length of the garage divided by the velocity, 12.5 nanoseconds. The car driver says an object, that's the garage, which was only 6 feet long, because it's shrunk, right, moved by a point, the front of my car. Okay? And so the time it took was the shrunken garage length, g over gamma, divided by v, only 7.5 nanoseconds from t. Okay? So the garage attendant says the time between 1 and 2 is 12.5 nanoseconds. The car driver says the time between event 1 and 2 is 7.5 nanoseconds. They're different, but that's okay, right? That's what relativity makes it be okay. What's event 3? Oh, you can guess this. Okay, the back of the car passes the front of the garage. All right? Now, we can calculate this in the same way. The garage attendant says an object, which is the car, which has length 9 feet, right? Because it's shrunk. That's L over gamma. Moves at 4/5 the speed of light past a point. I'm going from 1 to 3. So the garage attendant measures that with one clock, right? So just at one point. And so that time was 11.25 nanoseconds, and the similar kind of argument from the car driver calculates 18.75. So what is the answer? So the answer is if we look at it in events, that the time order of the events is different. The garage attendant says that event 1 happens, then event 3 happens, and event 2 happens, and these are the times between the two events. The car driver says they happen in a different order. Event 1 happens, then 2, then 3. Okay? So now the interesting thing here is to realize that what we've done is we've broken it up so the car measures the proper time for 1 to 2. The garage measures the proper time for 1 to 3. Okay? And all those numbers check out. So what we have here is we have just chosen a situation so that we have 3 events. One reference frame measures the proper time for one pair, and the other reference frame measures the proper time for the other pair. Okay? So there is really no paradox here. There is just no absolute answer to the question. Okay? If we say the car either fits in the garage or it doesn't, that's not a true statement. That concept of the car fitting in the garage is a relative concept. It has to be tied to a reference frame. Once I tie it to a reference frame, I can tell you the answer. According to the garage attendant's reference frame, the answer is yes. The car does fit in. And according to the car driver, the answer is no. Okay? But that's okay. It's exactly like the simultaneity Gedanken experiment we're talking about here. So that's okay. It's not a paradox. Here's a slightly different one. Famous rocket twin paradox. Suppose you have twins, and they take a ride on rocket ships here at relativistic speeds, and you have a rocket ship leaving the Earth, goes out, turns around, comes back to the Earth. When the rocket twin returns, is he younger, older, or the same age as his twin? Now, the question that we really want to ask here, is this just like the garage paradox, in which, okay, the rocket twin says he's younger than the Earth twin, and the Earth twin says the Earth twin is younger than the rocket twin, and everybody's happy and everything's okay. Okay? That's sort of the way we've been resolving these paradoxes. Don't worry, right? Everything's okay. Be happy. Okay? So now, the question is, does this question have an absolute answer or not? And I claim this is different. This is not like the simultaneity Gedanken experiment. This is not like the garage paradox, because when they're brought back together, they can't both say they are the older one. Because they're reunited at the same point in space. You can't have a relative answer about who is older. Who's got the gray hair? Who doesn't? Okay? It's obvious to everybody. Okay? So, I claim the answer is that the rocket twin really does return younger. Okay? Why, though? Can't we just use the principle of relativity to say that who cares who's moving, and therefore everybody comes back at the same age? That would seem like the obvious answer, right? If there's got to be a correct answer, it's and only one answer. It sounds like, well, maybe it must be that they come back at the same age, right? I mean, that's what I would guess. But then I would have guessed wrong, because I claim that the rocket twin really is younger. Why is that? Well, the key is there's a way of distinguishing between the rocket twin and the Earth twin. The rocket twin was accelerated because the rocket twin had to turn around. And when you turn around, you know it. Okay? And this acceleration, I claim, is the thing that distinguishes who was the rocket twin and who wasn't. Just thought of a great demonstration I could have done. Too bad. All right. So the way you do the calculation here is that we break this up, again, into events. Event 1 is rocket leaves Earth. Event 2 is rocket turns around. Event 3 is rocket returns. So the rocket twin measures the proper time for both of these intervals, 1 to 2, 2 to 3, because the rocket twin is present at event 1 and present at event 2. The Earth twin measures the proper time for 1 to 3. Okay? So that's the idea. I'm going to claim that, yes, if you got in a rocket and you went very fast, and you came back to Earth, you would, in fact, be younger than your twin. So now the question is, does this really happen? I mean, I've just told you stories, right? I mean, we're saying, if this is true, what I really said is, if this is true, this being Einstein's two postulates, then all these things would happen in this incredible fairy tale world where cars can move at 4/5 the speed of light and so on and so forth. The question is, does it happen in our world? Okay? Does it happen in our world? Well, you'd say, I certainly hope so. Otherwise, Einstein's just putting one over on us here, right? And I claim it really does. And the examples I want to choose, the first one is something called the global positioning system, which I think you're a little bit familiar with, for example. Jeremiah Sullivan, about 1 year ago today, in this very very place, right, gave one of these talks on the global positioning system, so I'm sure you remember absolutely everything he said. But I was able to go back and look and see what he said, and he mentioned this briefly, so I'll mention it a little bit more than briefly. What's the idea? The idea is you have systems of satellites that orbit above the Earth, and using those systems of satellites and some little, now even handheld device, you can find out where you are and what time it is, effectively, okay? And you can locate events on the Earth using these orbiting satellites. The satellites are orbiting at about 11,000 miles above the surface of the Earth. Now, what does relativity have to do with this? Well, those satellites are moving fast with respect to us. 12,000 feet in 1 second, okay? That's fast, right? 12,000 feet in 1 second. It's fast, but not too fast compared to the speed of light. The speed of light is 1 billion feet in 1 second, okay? So beta is the ratio of the velocity to the speed of light. So it's about 1 part in 10 to the 5th, right? 0.00001. So that's still pretty close to 0. And then gamma is 1 over the square root of 1 minus beta squared. You do that, you get this number. It's bigger than 1, all right, but there are about 9 or 10 zeros here before I finally hit a 5. So gamma is practically 1, man. Okay. But these satellites evidently live for about 7.5 years. So we can now calculate, right? We could do this calculation. If we know gamma, we could, this satellite's going around and around. It's moving at this gamma, with this beta of 0.0001. It has a gamma of whatever that is, just a little bit bigger than 1. And therefore, its time will be a little bit different from our time by this factor of gamma, right? And if you use this gamma and you calculate how many seconds there are in 7.5 years and you multiply them out, you'll find that the satellite ages 0.01 seconds less than its Earth twin, okay? It's a big deal. So why in the world would I have to worry about that? Well, before I go into that, I forgot there's one other thing. There's even a bigger effect, which I haven't talked about, and that's a part of general relativity from Einstein, and it's called the gravitational effect. Not only when clocks are moving with respect to other clocks, time is different. Moving clocks run slow. But also, if clocks are in a different gravitational field, they also, their rate of the ticking of these clocks depends upon the gravitational field. And those satellites are, as I said, 11,000 miles above the surface of the Earth, and that means that the gravity, the force on that satellite is going to be essentially about a factor of 15 lower than what it would be if the satellite were on the Earth, okay? And that means, that means it's in a different gravitational field, and therefore its clock is different by that way. It goes just the opposite effect, but it's about 10 times bigger, okay? So there's a general relativistic effect, which is about 10 times bigger than the special relativistic effect, and that's actually in the other direction. But it still sounds pretty small. I mean, 1/10 of a second in 7.5 years. Who really cares, right? Well, evidently, you care if you use a GPS system. If you're out in your fields and you want to know where the boundaries are of your whatever, you know, you have your little GPS in your tractor, right? And the problem is that GPS thing's got to know about relativity. Matter of fact, what happens is the clocks, what I understand, is that the clocks in the satellites are actually fudged so they don't tick at the same rate as the clocks on Earth by this small amount. And the reason it makes a difference is that if they didn't do this, if they just sent those clocks up ticking at the same rate as the Earth clocks when they were together, the claim is that the GPS determination of a position on Earth would be off by 14 miles in just 1 day. Okay? It's just because, you know, it doesn't sound like much, 1/10 of a second, 100th of a second, something like that, but those are the kinds of things you're actually using in order to determine where you are. So the amazing thing is, these wonderful little GPS systems have to know about relativity. If they didn't know about relativity, it wouldn't work, right? You wouldn't know where you are to 14 miles in a day. And I don't think they would sell very many of them. Okay? So relativity matters in our world. So that's an example of when the relativistic effects are small, but those small effects can be measured and used in our everyday world. Now, there's another world, which may not be real to most of you, but it's very real to me, and that's the world of particle physics. And here, the relativistic corrections are huge, right? And they're everyday phenomena, okay? So let's go into that a little bit. The experiment I'm working on here currently is at Cornell University. Here's Lake Cayuga in the background. This is alumni field, I think, and about 15 feet or so below the surface, there's a ring of magnets, which is the accelerator. This is called Caesar. The detector that we have is sitting over here, and that's called Clio. So there's Caesar and Clio. I'll leave it to you to figure out why they're called that. Then the particles that we use are effectively accelerated through 5 billion volts. Okay? So these particles are moving at not beta of 0.00001, but rather beta of 0.999999995. The gamma is not 1.00005, it's 10,000. Okay? So the gamma of what we're talking, the time for these electrons is 1/10,000th of the time that we measure. Okay? Now, this is something and if we didn't figure this out, we couldn't build such machines that are obviously very macroscopic in size. I've given here the website of our PR. We have PR for an experiment, right? Okay, and I've downloaded. It's got lots of information. I really don't have time to go into it too much, but I think where to do it? I've downloaded some movies from the website. For example, here is this is a flyby through the accelerator. We're going to start here at the electron gun. We're going to be accelerated through a linear accelerator. We're going to go into a synchrotron, which is going to accelerate these things up to 5 billion volts. And then they're going to be extracted into something called a storage ring, which they will then coast around. The electrons and the positrons, they're antiparticles. And then they will be brought together to collide. And then we have this big 3-story detector down here to see what happens when they collide. That's the big idea. Huge things. I mean, this detector is really 3 stories high. Okay? And we use it to study the very smallest things you can possibly study that needs relativity. If we ignored relativity, this would be a complete failure. So here's some cool graphics from our website. So this is a picture over here. This is the LINAC. Then it goes into the accelerator and then into the storage ring, where these electrons and positrons then are stored. That's why it's called a storage ring. They go around in opposite directions and are brought together to collide. But we've got lots of them, and not all of them collide every time. So we usually can use these things for half an hour, something like that, before we have to start the process over again. So anyway, enough of that. Here's what the movie looks like. Here comes this is the electron's eye view as it comes down the LINAC, and then it gets flipped into the synchrotron as it gets accelerated, and it finally ends up in the storage ring here, and then as it comes into here, it's starting to come into our detector. This is where the action is, if you like. This is where the collisions are. And then as they come in here and make their collisions, then we study it. Okay? So these, we have several of these little movies even on the web. And whatever it is, that's cool. All right. Now, that's sort of everyday occurrence. I mean, I could just stay here for hours talking about everything we do that needs relativity. But instead of doing that, I'm going to choose one experiment done by our colleagues here in nuclear physics at the university, which I think is the real rocket twin experiment. It's called the muon G-2 experiment, is its name. And what is it? This experiment actually was first done in the 1970s, actually at CERN when I was there. I didn't do it, but I happened to be there. And as I say, a new version intended to probe even further the issues that I can't discuss right now is being designed here and should be running soon. And what they're measuring, this G-2, is something called the anomalous magnetic moment of the muon. So they're not thinking about testing Einstein's special theory of relativity, right? They're doing something else. But they need relativity to do all their experiment, as we do. But actually, if you look at their data, a byproduct of their experiment is, in fact, a test of the rocket twin paradox. Let's see if we can understand that. What happens is they take muons of high velocity, 0.9995. That's a gamma of 30, right? So now what these muons are done, or they're made to travel in a circular orbit because they have magnets there that constrain the muons to a circular orbit. And then these muons are kind of their own clocks, okay? Because muons are unstable particles. They die. They decay radioactively into electron and some neutrinos. And they do this with a well-defined lifetime, okay? So what happens is that their lifetime, if you were to have a box of muons here and just watch them, then if you waited 1.5 microseconds, you'd have, on average, only half of them there. And if you wait another 1.5 microseconds, you'll have half of that, which would be a quarter of the original ones, and so on. That's what we mean by a half-life. So the interesting thing is, then, that these muons are basically carrying around their own clock. Their clock is, how many of my fellows are still hanging on, right? So if I have 1,000 muons, right, then 1.5 microseconds later, according to muon time, there will be about 500. Don't know which 500, but that's quantum mechanics, and we're not talking about that today. Okay? Then if I wait another 1.5 microseconds, then maybe there'll be only 250 of them. Okay? So the number of the muons that are there, it's like reading their wristwatch. Right? We can read their clock simply by saying how many of you guys are still alive. All right? So if that's true, and we've got muons that are going around and around and around in a ring, a circle, that means they're always coming back to the same point in space. That space is fixed to the Earth. Right? So we got the Earth twin is us sitting here, and the rocket twins are the muons going around. They're really moving fast. They've got a gamma of 30. Right? So what that means is their time is a factor of 30 different from our time. So what we should expect to see, what should we expect to see? If relativity is right, then what we should expect is that when we observe how many muons are still around, according to our watch, okay, there are a lot more. A lot more. We say the muons are living a lot longer because according to our time, because we know that they should die in every 1.5 microseconds, half of them should go. But in fact, what we should measure is now a new lifetime that's different by a factor, that's bigger by a factor of 30. So this is not some tiny effect. Instead of being 1.5 microseconds, the lifetime should be 45 microseconds. Okay? Anybody should be able to measure that, right? So it should be easy to see the difference. And in fact, here's a picture of the new ring that's being built at Brookhaven on Long Island. And there are magnets in here. The muons go around, they decay, and there are little stations all the way around the ring that measure the decays. So what you actually measure, this is data from the 1970 experiment, what you measure, in fact, is how many decays there are as a function of time. And here there's this graph really should be just exploded on out. You can hardly see it. Should be exploded out, out, and out, and out, because each one of these, it just, the number that you see just keeps going down, 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 and then it comes back here. This really should be connected onto it. There'd be some huge number of oscillations here. These oscillations that you see, if you can look carefully, that's the real point of the experiment. That is the measurement that they're trying to make. But if you forget that for a second, and in fact, well, I don't want to go there. As a matter of fact, if you just look at how this graph decreases in time, this is a logarithmic plot, semi-logarithmic plot, so it decreases essentially linearly. The slope of that line is the lifetime, and you can see that here's 1.5 microseconds is hardly on this scale, and we certainly haven't lost half of them by that time. I mean, 45 microseconds is out here someplace, and yes, this is about a factor of 2 lower than that. So we see immediately that, yes, the muons do appear to have a much longer lifetime. They are the rocket twins. They do move around. The data are in excellent agreement, better than 0.1%, I say here, with the lifetime expected using the gamma of 30. Okay? So the muons are, this is really the rocket twin paradox, right? The muons are moving around, they're constantly accelerating because they're moving in a circle. If they're moving in a circle, their velocity vector, even though their velocity magnitude may not be changing, but the direction is, that means they are accelerating, therefore they are the rocket twin. That's why we know they're the one who's going to come back younger. Okay? So, yeah. Yeah. Yeah, those oscillations have to do with something called the spin of the muons, which is, again, a totally relativistic effect. It's something that belongs to the muon, and there's a correlation, if you set everything up right, between, as the muon goes around a circle, the spin is also going around in a circle, and these oscillations are due to the fact that there's a correlation between the frequency of the so-called cyclotron frequency of rotation of the muons in the circle, and the precession of the spin in the given magnetic field. So but by setting those upright, you can measure directly G minus 2, the difference of the anomalous magnetic moment of the muon and the value 2, and that difference tells you all sorts of things, possibly lets you look into the future about developments in particle physics. But the reason all that works is that you're measuring precisely G minus 2, and you can measure so that and the answer is very close to 2. So you're measuring a very small difference, but you're measuring it directly, and I think it's something like the hoped for precision in this experiment. Remember, Al, maybe a third of a part per million or something like that. It's parts per million is what they're measuring it to. And that's what allows them to probe these other parts of the so-called standard model. So that might be a good topic for another Saturday morning thing. You can get some of our nuclear friends to tell you about G minus 2. I'm just using it to show time dilation. So I'm walking, they can run. Okay. So my conclusion from this talk is that if we accept, what do we need? We need Einstein's definition for the simultaneity of spatially separated events. Remember this. If I'm halfway in between, I get light pulses from both events at the same time. They happen at the same time. And we believe Einstein's two postulates, which are the principle of relativity. There are no preferred reference frames. Right? I only need one physics book. The results of experiments in one frame are independent of the translational motion of that frame. And the constancy of the speed of light. In fact, the speed of light is the speed of light, is the speed of light, is the speed of light, is the speed of light. Speed of light is the speed of light with respect to all observers. If that's true, then we are forced, I claim, it's funny, isn't it, from just physics stuff, to abandon our common sense notion of the absolute nature of time. Time is something being out there, independent of us, absolute, and just rolling along like a river. Okay? All our current experimental evidence supports all of these consequences of Einstein's postulates. Therefore, I think we must conclude that my time is not your time. Thanks a lot.